Okay, so welcome back. We are now on 214, which means we are doing modeling with logs, which means we're doing regression. Okay, this is different from when you were given a table of values and told to write a log function, right? No calculators involved, because those involved things like horizontal and vertical shifts that we had to actually include when we wrote it. So that's sort of looking at the pattern. Now we're going to be talking about actually using the calculator, Desmos or the graphing one, to write regression values or write regression equations rather for logs. And that is something uniquely different because they are written in a very specific way. Okay, so big thing I want you to take away from this though is that the description that you are going to be using, if you are trying to justify that something is logarithmic, then what you're going to have to use as far as the wording is going to have to be the input values are proportional or multiplicative over equal length output value intervals. So everything else we've done before this, exponential, linear, quadratic, they've all been equal length input values, right? But now they've changed. Now the outputs, right? We were talking about them being linear or arithmetic, where they were being added. Described in the same way we would before. You're describing your outputs now as equal length output value intervals, okay? And your inputs change proportionally or multiplicatively. Now take a look, your logarithmic model, and I know Logan had asked about this when we were first writing those equations in 210 and 211, that if you do a regression on it, this was the form that you were getting. You were getting an a plus b natural log of x or an a plus b log base 10 of x, because that's what the calculator does. It's not going to write it in that form that has like horizontal and vertical shifts, okay? So now we're actually going to be doing regressions on this. So good news is this is a prime example of an open response question. Notice they give you the form that they want you to write the equation in. Okay, it's not like you're going to have to memorize this. They give it to you. Okay, and again, when they tell you to write two equations that you can use to solve for A and B, all they're asking you to do is plug in the input and the output value for the 2 points into two different equations. You are literally replacing x and L of x, and that's it. So you can write this as 3 equals a plus b natural log of 2, and then 7 equals a plus b natural log of 5. And you can flip it around the other way if you want, you know, a plus b natural log of 2 equals 3. It doesn't matter, okay? So those are my two equations. And that's all you really ever have to do is you're just replacing with the points that they've given you, right? Your input and output. Now, the cool part about these is that you can actually treat them like a linear system like we did with the arithmetic sequences. You can actually subtract, right, these two equations. And by the way, I'm going to subtract them the other way because, you know, I want the bigger number. You can subtract them just like you would arithmetic sequences, right, to get rid of one variable, which is kind of the point. So let's see, 3 equals a plus b natural log of 2. And I'm just going to subtract these. And when I subtract them, my a's are going to cancel and I'll be able to solve for b. Okay, so if I subtract these, then I get 4 equals b natural log of 5 minus b natural log of 2. Now remember, I can't subtract those. Number one, I don't know what b is. And if I'm subtracting natural logs, written out like this, it technically means that I'm dividing them, right? So let's simplify that a little bit. 4 equals, I could take the b out, by the way, since I want to solve for it. Natural log of 5 minus natural log of 2. Can do that since they both have a b on them. All right, let's keep simplifying. That's going to be 4 equals b times the natural log of 5 over 2. Right? That's what we're allowed to do with those pieces. And to get b by itself, that basically means I'm just dividing by those natural logs. Now, I'm going to put this in the calculator to get the decimal form of this. All right, so I've got my calculator pulled up, so follow with me. Again, I'm going to do 4, and I'm going to put it in as a fraction. So that's control divide, right? And then here, I'm going to put the natural log that's over here on top of the x. So the natural log of 5 divided by 2. Close the parentheses, hit enter, And there is my B value. Just as easy as that as far as simplifying. Again, you would be expected to use a calculator for this. So 4.36543, and it doesn't look like it's rounded. It looks like it's actually there. So B equals 4.365, I believe it was 43, right? 43? 36543. Okay. So now I can plug B in to either one of my original equations, right, to go back and then solve for A. So the choice is yours. I'm going to use the top one. So just 7 equals A plus 4.36543 times the natural log of 5. Now, if you remember correctly that anything you put in front of a log is technically an exponent, right? And I also need to get A, by itself. So I need to subtract this whole thing. So this is going to be 7 minus 4.36543 natural log of 5. Now, I could type that in as is. I don't think that's going to be an issue. Let's check it real quick, because the calculator does know what the actual rules are. So 7 minus 4.36543 times the natural log of, what was the natural log of? 5. Yes, okay, 5. And 5, close the parentheses, should be good. And yep, there's my A value. Now, if we had changed that into an exponent, it should actually be the same thing. So let's check. 7 minus, because the rules do work, the natural log of, 5, and then raised to the 4.36543 power should be the same thing. Nope, didn't want the extra parentheses. Yep, see, same thing. The rules still work. So you could simplify it as a exponent, and it would still give you the same answer. So A is negative 0.02. We're going to call that 59. So A is equal to negative 0.0259. And you've done it. Again, this is all just using the calculator. That's what it's for in this case, because this is not something you're going to want to do, without a calculator. Okay, and again, you can use the Desmos for this as well. It will regress and give you the same values. And in fact, since you're using log and natural log, the Desmos calculator will work very nicely, because that's what it works in. It doesn't work in all those other log bases. All right, so let's try a slightly bigger problem. We're actually going to type this one into the calculator, or again, in Desmos. In the Desmos, you do need to make sure you click that little box after you've done your regression that says log-based, and then you should get the same values that I do. So let's go ahead and type these numbers in. Let's see, I need another page, and it needs to be a list and spreadsheet page. Yep. All right, so 75 and 120. Again, just follow along. 300, 450, 650, 900, 1500, 2500, and 5000. And then we're going to call that our input. So we're going to call that our X. That was not what I wanted. X. Okay. And then the Y values starting at 75. Let's see, it's 42, 58, 70. Oh, okay, so going up by that much. 79, 86, nope, 88, 95, 110, 125, 138, and 175. And again, nope, I missed one. Let's see, that's 175, so let's go back up. 138, I had to have missed one. 125, 110, that's the one I missed. Okay, so So I'm going to call that one Y. All right, so hopefully we remember the rules as far as what we need to do. We need to add a page that is a stats page, and we need to make that our X and that our Y. Okay, so I already know for a fact that it's going to be log. I can tell by the look of it. So I'm going to go to my menu, and I'm going to do, I believe it was analyze. Yes, I need to run a regression on it, and it's going to be specifically a logarithmic regression, and there's my equation. All right, and if I wanted to see my residuals, I could do that. Okay, so that should be my equation, where A is negative 91.5420, roughly, and B is 29.9088, again, roughly. Okay, so that's it. That was the equation. Now, again, we do need to write it in words. We've talked about this. There's very specific ways these get written. So we're going to find the equation, and A again is negative 91.5420 plus 29.9088. What am I multiplying that by? The natural log of P, and in this case, P is the church size. So the natural log of church size equals the, hopefully you remember the word, predicted average salary. Because that's what we are actually trying to predict, is the average salary of a pastor based on the size of their church. So the church is 500 people, so we're going to substitute in 500. 29.9088 times the natural log of 500, and whatever we get in the calculator is what it's going to be. Okay, so here you're not going to be able to do like find a table, I don't think. Let me check, see if we can actually do it. Menu. I'm betting it's probably not going to give me, yeah, it's not going to give me a table that goes with this. No, not even graph trace as far as that goes because of how far up it goes. So we're actually just going to have to go, have to go back to our calculator page and just basically type it in. So 94 point, oh wait, let's try that again. Negative 91, sorry, 0.5420 negative, weird. Okay, plus 29.9088 times the natural log of 500. And that should be 94.3295. So that should be my answer. And my answers, if you take a look back at the problem, are in thousands of dollars. So that equals 94 point, was it 3295. 3295, since we always put units on there, $1,000. So $93,000. Okay, so not too bad. Again, pretty straightforward. We've done regressions before where it's not that big of a deal. Now we're going to do the same thing with a little bit more of an applied instead of a table. And this is actually something that you do in science as well. I just don't know if you do it in log form. But this is something very, very common that we see in pre-calculus, that we're going to find out the decibel level of things based on a log equation. Okay, and again, they've given you the form that they want the equation written in. What you need to understand is that intensity is your input and decibels is your output. Okay, that's just reading the equation and realizing what I'm looking at. Okay, so we're going to do the same thing. We're going to write two equations. So the sounds of noisy traffic has an intensity of 1 times 10 to the negative fifth. So that's what's going in for the input. And an output is 70. So 70 equals a plus b. Now notice this is log base 10 instead of natural log this time. There's a reason for it. Log base 10 of 1 times 10 to the negative fifth, which is basically 10 to the negative fifth, right? All right, that actually can be simplified because this is log base 10, and the 10s would cancel each other out. So what you actually have is 70 equals a plus b log of negative 5. Oh, excuse me, not even log of negative 5, just negative 5. Because again, log base 10 of 10 would be 1, and then all you would have left would be negative 5. My apologies. Okay, so the other equation is going to be 120 equals a plus b log of 1. And log base 10 of 1 is, hopefully everybody remembers 10 to what power is going to equal 1 is 0. So this is 120 equals a plus b times 0, which means that a is 120. Okay, and again, this is just because this is done in log base 10, and that's how intensity is ranked, is in base 10 things. So it actually is kind of nice. It cancels out for you. So I know that a is 120, so now I can plug it back into the first equation. 70 equals 120 plus b times negative 5. That's just negative 5b. Subtract 120. That's going to be negative 50 equals b times negative 5, which means b has to equal 10. So you've basically found the constants for that formula. That 120 is your baseline decibels, and that b is 10, which is, kind of nice when you're talking about 10 times log base 10 of something. Okay, so we're going to actually use this to now solve. Okay, so the human eardrum, notice this is not a negative anymore, this is a positive. The human eardrum can burst when sounds reach an intensity level of 1 times 10 to the fourth. Now that's, that is the I level, and we are trying to work backwards to find the output. Okay, so going back to the equation as far as how it's written, the output, or B of I, right, equals, we now know what A and B are, 120 plus 10 times the log base 10 of, well, my intensity is 1 times 10 to the fourth, which is, I'll show it to you, it's 10 to the fourth, right? So we know log base 10 of 10 cancels. So what you have technically is your output equals 120 plus 10. Well, log base 10 of 10 to the fourth is just 4. So your output is actually 120 plus 40, so your output is 160 decibels. So your eardrums can actually rupture or burst when you're exposed to 160 decibels frequently. So that is it for 214. Like I said, we're doing some basic regression. We're going to get into it more with 215, and we're going to talk about more semi-log plots. But for now, we are done.